Hello everyone, so we are back and we'll be looking at the second part of our Gillespie algorithm series, and this is the final part of the series, and the first part got some really great response. Anyways, an update for our channel is that you can find all our codes on the GitHub page, including this video's code, and you can find the link in the description box below, and it will be the same for all our future videos. So I hope you guys will like learning side by side as we explain, right? And let's not waste any time, let's begin. Okay, so in our previous video, we saw that there is something known as the reaction probability density function, right? And if we are able to sample tau, which is the amount of time no reaction has taken place, and if we are able to sample mu, which represents which reaction has taken place, we can determine a statistically accurate trajectory for the system, right? And we saw that this is our reaction probability density function, right? We went through all the theory, and in today's video we'll take a look at an example problem and try solving this. So it turns out that if tau and mu belong to a uniform distribution which ranges between 0 and 1, which is this one p dash, this is a modified form of this probability density function. Let's call this tau star, right? And if we call this smiley face, right? So smiley face can be easily sampled, whereas star cannot, it's not so easily sampled, right? So it turns out that the relation between smiley face and star is such that if we are able to sample epsilon 1 and epsilon 2 from a uniform distribution, right, tau is given by equation number 18, whereas we can predict which reaction has taken place, which is mu, using equation number 19. So if you have not understood so far, no problem, you can write down this equation. I think things will become clear when we look at an illustrative example. So finally we come to the algorithm itself, right, which is really exciting. So step 0, we initialize with some time equals t naught. Usually we take time equals 0, and in today's example we'll do that, right? And we will obtain all the stochastic rate constant, the state of the system, and the time up to which we want to observe the system. All right, so that's step number 0. And in the loop, right, we have 3 steps. So the first step is to calculate the rate of the reaction, h1 into c1, h2 into c2, and all these conventions are from the first video. So h1 basically represents the number of ways a collision can take place for a particular reaction, right? And we define a naught as the sum of all these terms, all the rates of the reactions. All right, and step 2, we have to generate two random numbers, epsilon 1 and epsilon 2, which belong to a uniform distribution, and we compute tau and mu according to the aforementioned equation 18 and 19. And we then, as step 3, we update the state of the system x1 and x2 and update time. So one while loop will look one loop, right? These 3 steps will look something like this. So at step 0, we initialize at time t equals 0, right? And then using this epsilon 1 and epsilon 2, we are somehow able to obtain how much time it takes for the first, rather how much time it takes for no reaction to take place, which will be tau 1, right? And using epsilon 2, we will determine which reaction has taken place. Say there are 2 reactions, right? And epsilon 1 gives us something such that we get mu equals 1. All right, so we'll find out that the first reaction has taken place, and then we go back and continue the loop until we reach time equals t, right? So we'll get tau 2, we will get a reaction. We know that the reaction takes place instantaneously, right? So yeah, so as I've already mentioned, the stopping criteria is how much time you want to observe, right? So like I said, we will take a look at an illustrative example, and everything will become clear. So this is the question. So let's imagine the following reaction takes place. A gives B, B gives A, and the stochastic rate constants are C1 and C2. We have been given the values of C1 and C2. This looks like maybe an isomerization reaction or whatever, right? So it said that we need to simulate using both deterministic equation as well as Gillespie's algorithm, which is a stochastic equation. And we have been given 4 different cases of initial conditions. And in the end of the day, I do need to tell you what the advantages of the stochastic method is, right? So I've just put in that question as well. So anyways, if you want to look at this question again, we have put the link in the description box. So when we look at this particular equation, we can just write down the deterministic formulation, which is dCA by dt equals this, right? And where xa represents the number of xa molecules and xb represents the number of xb molecules, right? And dCB by dt is given by this equation, right? So let's call it equation number 1 and equation number 2. All right, so let's move on to the MATLAB environment. All right, so let's first look at the deterministic formulation of our equation, right? So I have made these couple of codes which represent deterministic as well as the stochastic formulation. You can take a look at the code, and the link is in the description box. It's on my GitHub page, right? And yeah, so let's look at the deterministic formulation, and we have done this numerous number of times. We have done this in our previous ideal batch reactor case, ideal PFR reactor case, right? So we are basically defining the constants. We are defining the initial values given in the question. So let's look at the question once. So we can see xa naught equals 10, xb naught equals 0. Okay, so xa naught equals 10. We can just put this in, and we will observe it for t equals 10 seconds, and these represent the the equations dCA by dt, dCB by dt, and we are giving it initial uh, quantities of xa and xb, and finally we'll plot it. So let's just run this code, right? Okay, so we can see that this they get a constant value, right, eventually. All right, and now if we change xa naught to other values, right, say 5000 and 0, right? Let's just put this 5000 and 0. We can see again the same thing happens, just that the concentration, the scale changes, but the rest of it remains the same, right? We have basically this occurring and this occurring, right? Now let's look at the stochastic formulation of the same problem, right? So okay, so this is step 0. All right, so we are defining c1 c2 etc and all the initial values, right? So for the first one, I think this was 10 and xb naught was 0, right? So we have defined all the initial conditions, so we are done with step 0, and we are defining the initial values, right? And fine. So next we initialize a loop, right? And we say that while time is less than t, where time will be used to keep track of what time it is within the loop, right? Which time step we are looking at, and t is the total time up to which we want to observe, right? So we keep that stopping criteria, right? And okay, let's start with step 1. So step 1, we calculate the rate of the reaction h1 c1 h2 c2 etc, and for us h1 is the molecule colliding with itself, so we just write c1 into xa, right? And the second rate will be C2 into XB, right? And we write A naught is equal to the total sum of the two rates, all right? And next we go to step number 2, which is to generate random numbers epsilon 1 and epsilon 2, right? And epsilon 1 is equal to rand. Now what is rand function? Let's see. Now if I just write rand, it just gives me a random value between 0 and 1, right? So that's what happens. And we already saw from equation number 17, right? Rather equation number 18. Yep, equation number 18, that the relation between tau and epsilon 1 is this, right? And st is just used by me to denote time, right? And we are just updating time over here in this line number 38. And next we want to find out which reaction has taken place, right? So we are again calling another random number. Remember, we need two random numbers, epsilon 1 and epsilon 2, right? So now in continuation with step number 2, right, if epsilon 2 is less than or equal to rates of 1 by a naught, right, we go for this condition, and otherwise we go for this condition. So what do these conditions mean? We will understand by running the code, but first let me put keyboard here. So keyboard is usually used for debugging, but I find it useful to explain as well, right? So okay, for end of one loop we'll just write keyboard. All right, rather I'll keep it here. Okay, so I will run the code once. Okay, so okay, as you can see, C1 and C2 have been defined, right? We know that x naught, the initial x value is 10, right? So evidently C1 into xa will give 2, C1 into xa will give 2 into 10, right? And there is no xb, so it will be 0 into 1. So C2 into xb, the initial xb is 0, right? So a naught will be 20, right? Because a naught is the sum of the two rates, right? And what is epsilon 1? Let's see. So epsilon 1 is 0.6324, right? And we finally get tau equals minus 1 by a naught into log of epsilon 1. So where is tau here? Okay, so we can see tau. So no reaction has taken place for 0.0229 seconds. Alright, so from 0 seconds to 0.0229 seconds, no reaction has taken place and some collision has taken place. So now we need to find which collision has taken place. Now here is the fun part, right? We know that whatever value epsilon takes, right, it will range from 0 to 1, right? And since due to the fact that no reaction of B can occur, the only possible reaction that can occur is A to B, not B to A, right? So epsilon 2 will always be less than or equal to rates of 1 by A naught, because rates of 1 is equal to A naught in this case, right? Because it's C1 into XAI. So when collision does occur, right, XA will become, one of XA will become XB. So one molecule will be removed, right, and it will be converted into XA, while when it comes to XB, one molecule will be added to XB, and hence in the next iteration we will see that there is one molecule of XB and there is 9 molecules of XA. So we'll just do continue. So let's look at this array XA, right? We can see 10 molecules have become 9 molecules here, whereas for XB from 0 molecules it has become 1 molecule. All right. So in the second iteration, we can see that epsilon 1 is 0.2785, and using this condition we can see tau is equal to 0.0673, right? So in the first reaction we saw from 0 to 0.02 something, right? No reaction took place, and some reaction took place instantaneously. And in the next time step, right, we can see tau is equal to 0.0673. So the total time elapsed so far is 0.02 plus 0.0673, right? And two reactions will take place, right? And again, epsilon 2 is 0.5469. 2, we know C1 is 2 into 9, so rates of 1 is 18, and rates of 2 is equal to 1 into 1, because there's only one molecule of xp, right? So still there is more probability of the first reaction occurring, which is from A to B and not vice versa, if and only if epsilon 2 was greater than say 9 over wait 18 over 19, right? Only then the reaction would have been possible. But I'm pretty sure 18 over 19 is well above 90%, so this is 0 0.9. So only if epsilon 2 had been above 0 0.9 something, I think the second reaction would have taken place and we would have used the else statement. So we continue with this, and we iterate until our time reaches capital T, and that's when the code ends. So what's going on in step number 2? Okay, now let's divide the probabilities on a scale, and it'll be between 0 and 1. So when we select epsilon 2, right, it'll lie somewhere in between 0 and 1. Right, now let's divide this into two regions, right? We'll divide this one part of the first part of the distribution as probability of reaction 1 occurring, and the second part is the probability of reaction 2 occurring. Now as you saw in the first iteration, the probability of R1 occurring was 100%. So no matter what no matter what the value of epsilon 2 was, it will lie somewhere in between 0 and 1. So in the first iteration R1 occurred, right? And in the second iteration we saw that R1 is equal to 0.94, right, in the second iteration, and our random value was less than 0.94, so it was somewhere over here. So again it was less than 0.94. So had it been more than 0.94, which is 18 over 19, then we could have we would have randomly selected reaction number 2. So if in case you are looking at a system with more than two reactions, so this one was an easy case, and if there are more than two reactions we can just divide the probabilities in between 0 and 1. So if there are say three reactions, we'll just divide the space into three regions, right? R1, R2 and R3, right? So dot dot dot, right? And depending on what your epsilon to where it lands, right, we will select which reaction takes place. And it's the same thing for 100 reactions or 200 reactions, is the same thing. So it all depends on what your epsilon 2 is and where it lands, and we need to keep the ordering fixed. All right, you could keep R2 here and R3 here or whatever, but in the subsequent iterations we need to keep the positions of these reaction rates, rather the reactions fixed. So let's do quit debugging because we can't keep running the whole thing over and over again, and let's get rid of this keyboard. So let's run this particular thing, right? So we can see that our reaction is pretty chaotic in contrary with our deterministic formulation, right? And let me run it again. We can see the trajectory is completely different. So this shows the stochastic nature of our system, right? You can see it's changing again and again. It's not the same thing compared to the previous one. However, now let's do one thing. Let's compare deterministic as well as the stochastic, right? So we will run our previous deterministic equation, which is from the previous code, right? And we'll just comment this part. So you will find this version of the code on the GitHub page. All right. So yeah, I'll just move this. So let me run it again. Okay, so why has this occurred? We can see that the stochastic and the deterministic equations are converging because 5000 is a big number, right? But if, say, this was just 10, we will see that it will diverge, right? See, so we can see that the stochastic formulation and the deterministic formulation will converge as the number of molecules increase, which is something that we'll expect, right? Why do we use deterministic systems for a much larger system? Because everything averages out, and statistically, that's what will happen. The average of the process will happen, right? And now we have to address the last part of this particular question, which was, what are the advantages? Why are we doing this whole thing? Right, okay. So when we look at the deterministic formulation, let's run this, right? We can see that, look at the points that are generated by this. We can see that there are decimal points, right? And we don't want our answer in fractions, because it doesn't make sense to, you know, at 1.4 seconds, it doesn't make sense to look at 3298.7 molecules. How does that make sense? So the Gillespie's algorithm gives us a more, you know, sane version of what's going on, right? It gives us answer in terms of whole numbers, right? See, look at this. It's always in terms of whole number. And the second advantage is that, say our initial condition is at 10 and 5, right? So this particular point, as initial points, are actually also called as stationary points. Why? Wait a second, what's going on? Oh, rather I should write it this way, 5 and 10, right? So this particular initial points are also known as, because the derivatives at these points become 0, right? If you take a look at the deterministic equations. However, when you run it along with this code, right, we can see that, rather, even though the system starts at a, we get a statistically possible scenario, and not unlike the, I mean, the deterministic equation just shows us that there are no collision taking place at all, right? Because we can see that they're completely stationary. But that's not the case in when it comes to the stochastic system. So these are the two advantages. One, it gives us realistic values of the collision taking place, and two, it addresses the. Man, I really found this video challenging to make, and if in case you're new to this particular methodology of stochastic algorithms and you learned something from it and got a new perspective, well, mission accomplished. And for those of you who were struggling with this, I hope you were able to learn a bit more than what you already knew. So don't forget to like, share, and subscribe, and do follow our Instagram page. And thanks. Peace.